When we apply the AC signal Vi here, then this Vi will be distributed amongst the components coming in its way, as these DC supplies has been distributed amongst the components in its way that we have calculated by writing the Kirchhoff's voltage equation for these DC supplies. We are not going to write a Kirchhoff's equation for this AC supply. This will be done when we will be studying the AC load line. But for understanding, you must be knowing that this Vi will be distributed amongst the components in its loop. So part of this will be distributed here, and this will be the AC part, small VBE, which will be added with the DC VBE made by this already available here to make a total VBE here. For example, if for example when we apply Vi AC signal, the negative phase comes first. At its negative peak, the part of this negative peak AC voltage is being developing across base to emitter, and because these voltages are coming from a pure AC signal, that then it will be a pure AC VBE. So we can write small v small be, but DC VBE is already available because of these supplies. Here we already have. Then this AC VBE when added with VBE makes total VBE at this moment when all these supplies are available. So the transistor has to behave for this total VBE. It means that this DC VBE has been shifted when added with the AC VBE to make a total VBE here. Thus, the IC which was here at DC IC is now becomes total IC at this moment. It means at this point the IC VBE is forcing the IC to be this one. It means the IC is decreasing when we apply Vi and its negative phase is coming. So this reduced IC when flow from this output terminal, because IC is flowing from here to here, the voltages here will be reduced because IC reduced, IC multiplied by RC is reduced, so voltage across these resistance is reduced. Similar is the case for this one, because IC divided by alpha would be IE, and when it is multiplied by this RE, it will also decrease. So this 15 volt previously was 6.9, 4 and 4.1, but this 4.1 will be reducing. This 6.9 will be reducing. It means VCE is increasing because the sum of all these voltages should be equal to 15 volts. It means the as IC decrease, the resistance between collector to emitter is increasing, or vice versa. You can say IC is decreasing because of increase in resistance between collector to emitter. You can say that. Anyhow, here we can see as base to emitter voltage, whatever it is, DC, AC or total of them, VBE decrease, the input characteristics curves dictates that IC should be decreased, and this decreased in IC will decrease the contribution of voltages across RC and RE. So the contribution of voltage VCE will be increased. What I am going to say that you have a decrease in ACIC, which when added with the DCIC previously available with only the DC supplies, it makes total IC decreasing from the DC value, and the contribution here and here is decreasing, and then the contribution of VCE will be increasing. So VCE, when we had DC VCE here, it was 4 volts, and this IAC VCE, the increasing effects in AC VCE when added with the DC one, it makes the total VCE increased at that moment when the negative peak of a VI was present. So we can show this thing in our characteristics curve. This was your question point, right? When we had only DC supplies, VCE, DC VCE, all capitals, DCIC, all capitals. When IC decrease, you can see only from here, when IC decrease, this IC decrease from this point, total IC because of negative AC current, AC collector current, reduce this total current here. So you got increased in VCE. VCE was here, but now it is increased. So total VCE at that moment when you have a negative inputs phase, AC input phase, you are having positive VCE. Say, similarly, when the positive phase comes, then AC VBE will be increasing when it is added with the DC VBE. So overall VBE will be increasing. You was here with only DC, you was here when AC VBE was decreasing because of decrease in VI, but now you have increase in VI, positive phase of the input AC signal, you will be having a positive phase of the VBE contribution from this VI, and this will be added with this VBE to make total VBE here. So from above it will be pushing the Q point at the right side of VBE, and for movement of this VBE, because of this characteristics curve and movement of this DC load line, the intersection is becoming this. So as VBE, total VBE increased, IC increased, and this increased in IC will make more contribution across these resistances, because I into R is voltage of these resistances. So increase of these voltages will means, it means that the voltage across VCE will be decreased to have a sum of total equals to plus 15 volts. It means increase in IC is possible because of decrease in resistance between collector to emitter. We had internal resistance, we will discuss it later. So we can say that as well. But now you can see when VBE change, IC change in the same direction. VBE increase, IC increase. VBE decrease, IC decrease. And as IC increase, contribution of resistance voltage across these resistances will increase. VCE decrease. So VCE has a negative relation with the VBE and IC. So if we see this here as well, we can see that when IC increased from DC to this one because of the input positive phase, IC increase, VCE decreased. So when this decrease, VCE increase. IC increase, VBE, IC, Vin has the same phase, whereas VCE has reverse phase. So if we have more cycles, we are having the same results. So here you can see that at the output, if we want to check, we had output at this node and we had a capacitor at this terminal. So after the capacitor, you will be having only AC signal. This DC VCE will be will not be present here, because capacitor does not pass AC. So this is the way these coupling capacitors are used. It is actually coupled the AC signal from here to here, and also couple out only the AC signal, leave behind the DC signal. So it means if you check here, you will get a DC offsetted AC signal. But when after the capacitor, if you take it from with reference to ground, you are having zero here, and AC, this only AC VCE here. So this is our output, that we had given this signal very low amplitude signal, and we are getting this. And what is the amplification factor? How this load line is moving here, not here. And what is the contribution that VI is giving to this is AC VBE, and here and here and here. We will discuss it when we will be studying the AC load line. Till then, you have only make an understanding that how much is the contribution this Q point moves. And these load lines have when have an intersection with the characteristics curve, give you the exact value of these parameters. So you have analyzed a circuit, an amplifier circuit given to you, and you have found the load line like this, the Q point, this at the output side and at the input side. Notice that the designer had a choice of this VCC. The designer had a choice of this R out DC. This R out DC, remember, is contribution from this RC and RE here, and this R in is the contribution with RB and RE here. So it means the designer can have the slope of its own choice, can have VCC of its own choice, and same here.